Alright, welcome back to Inorganic Tutors Institute. This is the second episode of Practice Problems in Introductory Analysis. In this episode, we are going to solve 4 problems that will enhance our understanding in introductory analysis. So the first problem is we want to determine whether the below given series is convergent or divergent. And if it is convergent, then you want to find the sum. All right, so first of all, if you have a series problem, just look at it and see if it is a geometric series, right? So let me give you some secret tips before we start solving the problem. So, solution. Secret tips. 1. Looking for geometric series hiding under the exponents. Now, here is the logic behind what I'm trying to tell you. That you should look for geometric series that is hiding under the exponent. This is the logic behind it. The logic is that whenever whenever you have whenever you see or you have something like this, okay? So let's say that you have something like summation from n equals 1 to infinity of something over a number, okay? Something over a number to the power n minus 1, or say something over a number to the power n. All right, so whenever you see something like summation from n equals 1 to infinity of something over number to the power what, n minus 1, or something over number to the power what, n, then that is if it matches the geometric series, okay? So that is if it matches the geometric series pattern. That is where you have, the geometric series pattern is A plus AR plus AR squared plus that up to infinity, right? So this is the geometric series pattern, okay? So if you have something of this sort, summation from n equals 1 to infinity of something over a number to the power n minus 1, or summation from n equals 1 to infinity of something over a number to the power n, then you have to check if it matches the geometric series pattern. And you know that the geometric series pattern is this, right? So tip 2, or second secret, ignore the n minus 1 versus n difference at first, okay? Then you can you can always use the index, or just remember the formula. Okay, just remember the formula that still works, or just remember the formula that still works. Okay, that is the second secret. Third secret, you can split the sum. Okay, so as we have here, we can just split the sum into two parts. Okay, so third, split the sum. Okay, split the sum if there are two terms. If there are two terms inside. So this one, for instance, we have 1 and 2. So this is the first term, this is the second term. So we can just split this sum, and then it will make our work very much easy. So for instance, we can split something like summation into a plus b to be summation a plus summation b. Right, so that is the split session. That is the third tip. Now, each is usually a simple geometric series. Each summation is usually a simple geometric series. Okay? Whenever you split the sum, each of them represents a simple geometric series. And so it makes your work very simple. Now, the fourth tip, use the geometric sum formula. Use the geometric sum formula instantly if the ratio is less than 1. That is, sum equals a over 1 minus what? R. That is the geometric sum formula. So if the ratio is less than 1, then you can use this formula. Now, we have gotten all the tips that we need in this problem, or in a geometric series problem. So, let's consider the problem at hand and start to deal with it. So I can clean this, right? So now I want you to consider certain things before we start the process. Look, from here, we know that this is having, if the R is less than what? 1, then we can use the the geometric sum formula, right? The geometric sum formula, as we have here. Take note of this formula. That is what you use if the ratio is less than 1. Okay, so let's analyze the problem that we have. Let's analyze it. So first of all, okay, so we consider, since we are asked to determine whether it is convergence or divergence, and if it is convergence, then we find a sum. Then let's consider these steps. Okay, now we write the series in a standard form. All right, so we have to rewrite this series in a standard form. All right. So how do we do that? Recall that a geometric series has the form. So recall that a geometric series has the form summation from n equals 0 to infinity ar to the power n equals a over 1 minus what? R. And that is if absolute of R is less than 1. So take note of this. So you have to remember that the geometric series has the form this, and it is equal to what? This. And that happens if the ratio, right, is less than 1. The absolute of the ratio is what? Less than 1. Okay. So let's consider the first part of the problem. So we are going to say that summation from n equals 1 to infinity 1 over 2 to the power n minus 1 plus 2 over 3 to the power n minus 1 is the same as summation n equals 1 to infinity 1 over 2 to the power n minus 1 plus 1 over 3 to the power n minus 1. Okay, I'm trying to split it, all right? So n equals 1 to infinity 1 over 2 over 3 to the power n minus 1. So we have understood that if you have two terms inside the bracket, then you can split them as the third secret says, or the third method says. So we split them. We have been able to split them. So let's analyze them step by step. Consider this, analyze it, consider this, and analyze it. If each of them, the ratio is less than 1, then we can find the geometric sum. So let's go here. Let's go here. Let's go here. So we are going to consider the first part. So considering summation from n equals 1 to infinity 1 over 2 to the power n minus 1, right? So this is what we are considering first. Then we come later and do this, right? So first of all, we know that this we have right here is the same as summation from n equals 1 to infinity of 2 to the power negative into bracket n minus 1, right? This we have right here can be expressed as this, right? So once we know that this can be expressed as this, then we can go ahead and do the necessary. Okay, so this is the same as 2 to the power negative 1 times 2 to the power n minus 1. No, yeah, that would divide. That would divide, okay? That would divide. So we can say that this is divided by 2 to the power, yes, so that is it. That is it, all right? So we'll have 2 to the power 0 times half to the power n minus what? 1. So this is the same as this, right? Now, we can say that this, we know that 2 to the power 0 is what? 1. So we have summation from n equals 1 to infinity 1 times half to the power n minus 1, right? So we can basically write this as half to the power n minus 1, right? So this is what we have gotten so far. So for the first term, or for the first part of the summation, this is what we have. And we can see clearly from here, or even right from here, we can see that our A is 1 and our ratio, which is the R, is half, of which is less than 1. So this is what this first part of the summation or of the series converges. Now let's consider the last part of the series and see if that one too converges. If both of them converges, then we can find the sum. Okay, so let's try to find the sum for this one before we come to the second part of the problem, right? The second term. So sum, we know that we are going to use this geometric sum formula, right? So A over 1 minus R will be equal to, our A here is 1 divided by 1 minus what? Half. So we have 1 over 1 minus half is what? Half. And this is equal to 2. So we have our first sum for the first term to be 2. Now let's consider the second term. Let's consider the second term. So the second term, of which we have summation from n equals 1 to infinity 2 over 3 to the power n minus 1. So we know that this is basically the same as 2 times 3 to the power negative. So we have summation from n equals 1 to infinity 2 times 3 to the power negative. So we can actually write negative 1, right? But it's not necessary. So we write negative of n minus 1. So this right here is the same as this, okay? So once we have been able to express it this way, we have no problem again, right? We have no problem again. So we can equally say that this is equal to summation n equals 1 to infinity 2 times 1 over 3 to the power n minus 1, right? 3 to the power minus 1 is the same as, this one is the same as 1 over 3. And that is what we have right here. So this whole term has been formulated this way. So we can equally say that, the series becomes the series. So we can see that the ratio here too is less than 1. So here A is equal to 2, R is equal to what? 1 over 3, of which is less than what? 1. So we say that the geometric sum A over 1 minus R is equal to 2 over 1 minus what? 1 over 3. And that is equal to 2 over, that is equal to 2 over 1 minus 1 over 3 is 2 over 3. So we have 2 over 3 here. So basically we have 2 times 3 over what? 2. And this cancels this. So we have what? 2. We have 3 instead. 3. So the geometric sum for the second part is also 3. Okay? So we have 3. So the first part converges, the first part converged, and the second part also converged. And we find the sum for the first part, we had 2. We did the same thing for the second part, we had what? 3. So we are going to say that the sum is equal to 2 plus what? 3, and that is what? 5. That is so beautiful. That is so beautiful. So conclusively, we can say that both conclusively we can say that both series converges, right? Both series converges, and therefore we can say that the sum of which we had 2 and 3 is equal to 5, right? So conclusively, the series of which this was the series summation from n equals 1 to infinity of 1 over 2 to the power n minus 1 plus 2 over 3 to the power n minus 1 converges, and its sum is 5, and its sum is 5. Very, very, very interesting, right? Very, very interesting problem. So I've given you the tip that you need to be able to solve a geometric series problem. So once you have the pattern to be a plus ar squared to infinity, then you know that this is following a geometric series pattern. So once you know that it is following a geometric series pattern, then you follow the tips that I gave before we started solving the problem. Once you follow the tips, nothing becomes difficult again. So that is question number 1. Now give me some short break. I'll be right back with question number 2. All right, welcome back from the short break. I believe that you have been able to go through the very first problem and you are good with it. Great. Now that you are satisfied, let's go through the question number 2. With question number 2, we have been given this Sn plus 1 equals n plus 1 divided by what? N times xn. Now, we have been given S1 to be 1, and then we are asked to find Sn. So this problem, this kind of problem is one of the easiest that you can have, right, as a student. So let's begin with the process. So given that, always in introductory analysis, always try to write each step, write it. It makes sense. Write it. All right, so given that Sn plus 1 is equal to n plus 1 divided by n times xn, all right, when S1 is equal to 1, okay, when S1 is equal to 1, now we want to find Sn. So xn is a question mark. So as I said, it's one of the easiest that we can have. So how do we find Sn? First, okay, first of all, what we have to do is that we have to let n equals 1. We start from 1, all right, because they give us S1 is equal to 1. So we start from 1. Now we can't know the n of Sn. So we will do up to some point, then we end it there. Okay, so let's say we will do up to S5, then we end it there. All right, so first of all, let's consider when n is equal to 1. All right, so if n is equal to 1, we substitute into the equation that we were given. So we have xn Sn, now n is 1, so we have 1 plus 1 equals what? N plus 1, that is 1 times xn. Xn, so xn now is what? 1, so we have 1 here. Remember that from the question, x1 is what? 1. So we place it there. So now here becomes x2 equals 2 over 1 times x1 is now 1. So we have times 1. All right. So this implies that x2 is equal to what? 2 over 1 times what? 1. And this cancels this. So we have s2 to be what? 2. Very, very interesting. So you see, they gave you S1, you have obtained S2. Now, how do we get S3? Because we have gotten S2, we can easily get what? S3. So we consider when n is equal to what? 2. So when n is equal to 2, we are going to have S2 plus 1 equals n, which is 2 plus 1, divided by what? 2. Times xn, right? Now our n is what? 2, right? So we put it there. So we have x3 equals 3 over 2 times x2 was obtained as 2. So this implies that s3 is equal to 3 over 3. Yeah, it's going to give us 3 because this will cancel the, right? So we have s3 to be what? 3. Once we have S3, we can go ahead to find S4 as well. So now we consider when n is equal to what? When n is equal to 3, right? When n is equal to 3, then we find S4. So 3 plus 1 equals 3 plus 1 divided by 3 times xn. Xn, now n is 3, so we have x4 equals 4 divided by 3 times x3 now is 3, right? So we have 3 here. So x4 will be equal to, this cancels this, and we have s4 to be 4. Now, we have been able to find x4. Let's try to get s5, then we end it there because we can't go to infinity. So when n is equal to 4, then we have s4 plus 1 is equal to 4 plus 1 divided by what? 4 times x4. Now x4 is 4, so we have x5 to be equal to what? 5 over 4, then 4 here, right? So this cancels this, and then we have s5 to be what? 5. This is so brilliant. This is so brilliant. Now, since we have been able to find x5, we can end it there, because if we decide to do it, we can do it up to infinity. So we end it at s5, then we can say that our Sn is equal to, we start from where they give us S1 to be 1. So Sn is equal to 1, 2, 3, 4, 5, up to infinity. So we bring 3 dots at the end. So we say that thus Sn is equal to 1, 2, 3, 4, 5 dots, dot, dot, dot. Right? So Sn is equal to 1, 2, 3, 4, 5, comma, 3 dots. It means it goes up to infinity. We can't go up to infinity. If we are human beings, if it is computer, maybe it can go up to where maybe it's tired, then it will stop there. But let's stop at S5. All right. So Sn is equal to 1, 2, 3, 4, 5, up to infinity. So that is question number 2. Now give me some short break. I'll be right back with question number 3. All right, welcome back from the short break. I believe that you have been able to glance through problem number 2 and you are good with it. Great. So now that you agreed with me on question number 2, let's look at question number 3, where we are asked to find the radius and the interval of convergence of the series right here. Now, given a problem of this nature, how do we go about it? So first of all, let's write the problem. So given that summation n equals 1 to infinity -1 to the power n divided by n times 5 to the power n x to the power n. Right, so a problem of this sort, how do we handle it? So first of all, I want to give you some steps before we start solving the problem. All right, so first of all, let's try to identify what kind of series is this, right? What kind of series is this? So first step is to identify that what kind of series is this, right? That is the first step. So identify what kind of series is this, right? Now, once you have been able to identify the series, right? 2, and clearly from here, this is a power series, right? This is a power series. This is a power series in X, right? This is a power series in what? X. All right. So once we have been able to know that this is a power series in X, then what can we do? How do we know that? How did we know that this is a power series of X? We knew that this is a power series of X because 1, it contains X to the power n. This is power, and this is what? X. So it contains X to the power what? N. 2, it's summed from n equals 1 to infinity. So this is first identification that it is a power series. This is second identification that it is a power series. 3, general form of a power series. Now, why does this step matters, right? Why does this step 1 matters? So basically, the purpose of this step 1 is 1. Once we know that it is a power series, then we know that if the absolute of X is less than the ratio, then it will converge, right? So once it is a power series, then it converges for absolute S less than what? The ratio, right? 2, it diverges for absolute S greater than the ratio. Then the third one is we must test the end points, right? The end points separately. We must test the end point separately. That is the third one. Now, that is the main reason why this step 1 matters. Once we know that it is a power series, 1, you have to know that it will converge for absolute x less than what? R. It will diverge for absolute x greater than R, and we must test the end point separately. Now let's consider the second step. So step 2. So the step 2 is where we are going to use the ratio test to find the radius of what? Convergence, right? So using the ratio test to find the radius of convergence. That is what we are going to use to find the radius of convergence, the ratio test. Now, why are we going to use the ratio test? Why not any other method than the ratio test, right? So why are we going to use the ratio test? So the reason is very, very simple. The reason is very, very simple. One, it is because the series involves powers, right? The series involves powers, right? So because the series involves powers like x to the power n, 5 to the power n. From here, x to the power n, 5 to the power n. It involves powers. That is why one of the reasons why we are going to use the ratio test is that it involves what? Powers. And the ratio test is the efficient way, or is the efficient tool for the power series. Is the efficient tool for the power series. So you see, it's very simple. Oh? You have to understand the process. Once you understand the steps, all right, there is nothing that will hinder you from doing any problem that involves such ideas. Now, what are we going to use? What are we going to do? Once we have been able to know the first step and know what it goes into the first step, and we know the second step of which we know what it goes into the second step as well, then now let's apply the ratio test to start the process. All right? So we are going to apply the ratio test to start the process. So we say that applying the ratio test, we can say that a sub n, of which we identified, okay, we have cleaned it. We say that a sub n, right? We identify the a sub n here to be a sub n to be equal to negative 1 to the power n divided by n times 5 to the power what? N. That is the a sub n we did earlier on, right? So now, what we are going to do is basically use the ratio test, all right? We are going to use the ratio test to, determine the radius of what? Convergence, right? So, applying the ratio test, we say that let a sub n to be equal to negative 1 to the power n divided by n times 5 to the power n. And a n plus 1 will be equal to negative 1 to the power n plus 1 divided by n plus 1 times 5 to the power n what? Plus 1. So this is our an and this is our an plus what? 1. So we are going to follow the process and it's going to make the work so easy. So let's go away with this. Let's go away with this and see what we can do. So basically, so once we have been able to state our an plus 1, then we say that thus our r, which is the radius of convergence, is equal to an divided by an plus 1. So that is how we are going to deal with it. So you see, the work is going to be easy. Once you have been able to identify your an and identify your an plus 1, the rest is what? Algebraic manipulations. So from here, we see that this an is negative 1 to the power n divided by n times 5 to the power what? N. Or divided by negative 1 to the power n plus 1 divided by n plus 1 times 5 to the power n what? Plus 1. And all are in the absolute sign. So this is what we are going to do. All right? This is what we are going to do. We are just going to simplify this algebraic expression and then that's it. So we say that this is equal to, so let's apply the limit on them. Okay, let's apply the limit on them. So we basically put the limit there, or we can decide to put the limit at the end of the work. All right, so here n approaches what? Infinity, right? So that is the ratio test. So we have that. So we can say that our ratio, radius of what? Convergence is equal to what? Limit as n approaches infinity of negative 1 to the power n divided by n times 5 to the power n divided by, you know, all this big division, we are going to turn it, right? So we have negative 1 to the power n plus 1 divided by n plus 1 times 5 to the power n plus what? 1. Right, so this will give us limits as n approaches infinity of negative 1 to the power n divided by n times 5 to the power n times, right? I'm using dot as a multiplication sign, right? So this will go up and this will come down. So we have n plus 1 divided by negative 1 to the power n plus what? 1. Right, so we proceed up here. So we proceed up here and we say that radius of convergence will be equal to limit as n approaches infinity into brackets, that is absolute sign, right? We know that this is negative 1 to the power n divided by n times 5 to the power n multiplied by n plus 1 times 5 to the power n plus 1. So let me write the whole thing again before we start, all right? So that it becomes easy for our, right? Okay, so this is what we have. So from here, we can say that limit as n approaches infinity of this now becomes times, this is n plus 1 times 5 to the power n times what? We apply indices here. You know that 5 to the power n plus 1 means that 5 to the power n times 5 to the power 1. So we have 5 to the power 1 here, divided by negative 1 to the power n times negative 1 to the power 1. So the same indices we used at the denominator as well. So we have limit as n approaches infinity, negative 1, right, to the power n times n plus 1 times 5 to the power n times 5 divided by negative 1 to the power n times negative 1, right? So here we say that our radius of convergence is equal to limit as n approaches infinity of, you know that this can take off this, right? Very simple, you understand that. So this also takes this, okay? So now we have 1 over n times n plus 5, n plus 1 times what? 5 divided by negative 1, right? Very, very interesting. So now we can say that we have, as n approaches infinity, now this becomes 5 into n plus 1 divided by what? Negative 1 into what? N. Right. And we know that this is into bracket, right? 5 into bracket n plus 1 divided by what? Negative n, right? And this can be expressed as limit as n approaches infinity, of 5 divided by negative n times n plus 1 divided by what? Negative n. Right? So that is what we have at this point. Now we know that this one that we have right here, okay? All right, so let's do something here. Let's remain it there and come here. So now we say that our radius of convergence will be limit as n approaches infinity, absolute of, we can express that we have here as 1 over n times n plus 1 divided by what? Negative 5. A? Is it negative? No, this part is, right, this, right, divided by negative 1. Okay, so this is basically 5, okay? So we chose to write 1 over n separately, right? 1 over n separately times 5 into n plus 1 divided by what? Negative 1. So from here, we can say that this we have right here, we can expand the bracket, right? So when we do that, so we have this to be n approaches infinity of 1 over n times, this will be 5n plus 5 divided by what? Negative 1. Okay, so this is what we have right now. And we know that this we can basically now multiply, right? So when we do that, we have limits as n approaches infinity of 5n plus 5 divided by negative n, right? So this negative right here, okay, this negative right here is affecting everything at the numerator, right? So we're going to have radius of convergence to be equal to limit as n approaches infinity of negative, right? We bring the negative in front of all. So we have negative of n plus 5 divided by what? N. Right? So at this point, we can just remove the absolute value. Absolute value. So when we remove the absolute value, then we can now have a positive result. We can have a positive result. So we do that by removing the absolute value. We are going to have the radius of convergence to be lim at n approaches infinity 5n plus 5 divided by n. So this is what we have right now. So you know that when you move the absolute value, this is what you have right now, right? So we are going to have radius of convergence to be equal to limit as n approaches infinity. You know that this denominator can split the numerator into 2, right? So we have 5n divided by n plus 5 divided by what? N. Okay? And this clearly shows that we have this right here. We're going to have 5 because this will cancel this. So we have 5 plus 5 over what? N. Now, as n approaches infinity, so we have radius of convergence to be equal to limit as n approaches infinity of 5 plus 5 over what? Infinity. Now, what is a number over infinity? A number over infinity means it is approaching what? 0. So we say that that becomes 0, right? So we say that we have this implies that 5 over infinity is what? 0. So we have our radius of convergence to be limit as n approaches infinity 5 plus what? 0. So we have radius of convergence to be limit as n approaches infinity of 5. And we know that limit of a constant is the same constant. So we have, this implies that our radius of convergence is positive 5. This is so amazing and it is so easy to do. So now that we have our radius of convergence to be positive 5, what are we going to do? This basically implies that, remember, when we're doing it, we had an absolute sign in it, right? So this basically implies that, so this implies that absolute of x minus x naught must be less than 5, right? This basically implies that absolute of x minus x naught must be less than what? 5. So this means that if s naught is equal to 0, then we're going to have absolute of x minus 0 should be less than what? 5. So this statement right here means that you have negative 5, right, in the absolute sign. So in the absolute sign means that you have this, if you remove the absolute sign, you have both negative or what? Positive. So we have negative 5 less than x minus 0 less than what? 5. Okay? So we have negative 5 less than x, because if you add 0 here, you're going to have the same thing. If you have 0 here, you're going to have the same thing. So we have this. Okay? So this implies that our he had our radius of convergence to be what? 5. And this is what we have. So the interval is minus 5 less than x less than what? 5. But we are not sure that this is exactly the interval. Rightly done, we know that the radius of convergence is 5. But we are not very sure that the interval will fall within these ranges. So we have to go and test, right? You have to go and test using the question, right? You have to go and test if it will work, or the two will work. So we come up here, then we test. So we say that when x is equal to -5, what are we going to get for the interval? Is it going to fall in it or not? So we apply that and check, right? So we say that summation, the question gave us summation n equals 1 to infinity of -1 to the power n divided by n times 5 to the power n x to the power what? N. Right, so we are saying that if x is equal to -5, then what will happen to the series? Are we going to have the result that will fall within this range? Let's try. So we are going to have summation n equals 1 to infinity -1 to the power n divided by n times 5 to the power what? N times, now x is what? -5, so we have -5 to the power what? N, right? And this, what can we do? Can we simplify this? Yes or no? Right? That is a yes or no question. So we say that this is equal to -1 to the power n times -1 to the power n times what? 5 to the power what? N. Right? So we are going to change this right here to positive, then we multiply in front by -1. So we have -1 to the power n times 5 to the power what? N. This and this is the same as this, right? Divided by n times 5 to the power what? N. So that we can have something cancel something. So we can see that this cancels this. So we have something, this right here, -1 times -1 to the power n divided by what? N. And we know that indices says that if they have the same basis and they are multiplying, we add the exponents, right? So we have -1 to the power what? 2n divided by what? N. Now, this expression we have right here is the same as summation n equals 1 to infinity -1 to the power n all squared divided by what? N. This expression is the same as this. Beautiful. So now that we have been able to, okay, let's write this here first. So this is the same as this, all right? So now that we have been able to do this, we know clearly that everybody knows that a number, a negative number squared will result in positive, right? So we have summation n equals 1 to infinity of -1 squared becomes +1, right? Then we have to the power n divided by what? N. That is so interesting, right? So this is what we have at this point. Now, what are we seeing right here? We can see that, 1 to the power anything is what? 1. So we can see clearly that this is the same as summation n equals 1 to infinity 1 over what? N. And this is symbolizing something, right? This is symbolizing something. This is symbolizing something. Can you type it at the comment section? What does this symbolize? So basically, this is telling us that our P here, you know that it's something like this. This is like a harmonic series, right? And P here will be 1, right? So this is telling you that the P here is 1, right? So that's P is equal to what? 1, which is not greater than what? 1, all right? And here we can say that hence by the P series test, summation from n equals 1 to infinity of -1 to the power n times -5 to the power n divided by n times 5 to the power n diverges, right? It diverges. It diverges, right? It diverges. So remember from the earlier note that we did, we said that if the ratio test is less than 1, then it is what? It converges. But if it is greater than 1, then it's what? Diverges. So that is what we are having here. So this one, when x is equal to -5, it is a divergent, or it is diverging, right? It is diverging from the series. So this is divergent right here. This is divergent. Now, let's consider when s is equal to what? +5. So we consider when x is equal to +5. We consider when s is equal to +5. So let's conclude. So we can say that therefore summation from n equals 1 to infinity of -1 to the power n x to the power n all over n times 5 to the power n, right, diverges at x equals what? -5. Great. So we have done the first part of the interval. The second part is what? When x is equal to what? +5. Right? So we are going to consider when x is equal to what? +5. So in that instant, we are going to fix it inside and see what it will give us as well. So summation n equals 1 to infinity -1 to the power n. Now s is what? +5. So we put +5 there to the power n divided by n to the power n. Right? So this basically reduces to this right here, and know that this will cancel this. So we have -1 to the power n divided by what? N. Right? That is what we have. Now we know that this right here, there is no way this right here will give us a positive value, right? There is no way this right here will give us a positive value. So we can say that let xn, right, let Sn equals 1 over n. All right? So we say that this implies that Sn plus 1 will be equal to 1 over n plus 1. Right? So that's Sn plus 1. Sn plus 1 is less than or equal to Xn. Right? Sn plus 1 is less than or equal to Sn. So we say that hence Xn, hence Sn is a decreasing sequence is a decreasing sequence, all right? And also is a decreasing sequence is a decreasing sequence, and also limit as n approaches infinity of Sn is equal to limit as n approaches infinity. Sn here is what? 1 over 1 over n is equal to 1 over n, right? So we know that when n is infinity, then we're going to have limit as n approaches infinity, 1 over infinity. 1 over infinity is what? 0. So we have limit as n approaches infinity of 0. Limit of a constant is the same constant, of which we have what? 0 there. So we can say that by the alternating series test, right, you can see that this right here, I didn't mention it earlier. This right here was following the alternating series test. So from the beginning, the first one that we did, the resultant, this one that we had, was following the what? The harmonic series, and it diverged, right? It diverged, right? Now, this one that we had, it is following the what? Alternating series. So we say that thus by the alternating series test, we say that summation from n equals 1 to infinity of -1 times x to the power -1 times 5 to the power n divided by n times 5 to the power n converges, right? Converges, right? Because we had the limit to what? 0. So it converges, right? So we can say that hence summation from n equals 1 to infinity of -1 to the power n x to the power n divided by n times 5 to the power n converges at x equals what? 5. Converges at x equals 5. So the first one we had diverged at x equals what? -5. And the second part at x equals +5, it converged. So what are we going to write as our conclusion? So we say that therefore the interval for convergence, is -5 and +5. Now, the first one diverged, so we are going to have an open bracket. Then the second one converged, so we have a closed bracket. So this is how you present it. If you have a diverged one, then the bracket is going to what? Open at that side. If it is converging, then the bracket is what? Going to close. So that is for this particular problem. So you see how the problem is. It's so interesting, but you have to follow the principles of the series, the power series. And if you're able to follow the principles of the power series, you're good to go. And you realize that in this particular problem, we didn't only use the power series. We came across harmonic series and we came across alternating series. So you have to understand the behavior of each of the series. Now, this is question number 3. Give me some short break. I'll be right back with question number 4. welcome back from the short break. I believe that you have been able to digest the question number 3 and you are good with it. I believe you are completely agreeing with me that it is the right process, and you agreed with me that we are on the same wavelength. Now, with question number 4, we want to use the comparison test to determine the convergence of this series, right? So this is the series that we have been given, and we have been given the rule that we should use the comparison tests. All right, so how are we going to do that? First of all, we have to write the problem. I always say that if you are dealing with intro analysis, make sure that you write every step, right? So given that summation from n equals 1 to infinity of n minus 1 divided by n cubed plus 1, then we can say that we have to let Sn represent the function that we have been given, right? So let Sn represent the function that we have been given, right? So once we have been able to let Sn represent the function that we have been given, then the next step is going to be where we say that Yn should be equal to what? N minus 1 divided by n cubed. So Yn is equal to n minus 1 divided by what? N cubed. Right, so this is the ratio test approach. So first of all, you let the whole of the function that you have been given represent what? Sn. And then you reduce the denominator by 1 to let that one represent what? The Yn. Alright, so once you have been able to do that, the next step you have to follow is to make sure, you know that the reason why I reduce the Yn by 1 is just we want to make sure that the Sn is less than the Yn, right? So we say that Sn is less than or equal to Yn, right? So once we do this, we know that definitely the Sn will either be less or equal to this, because if, for instance, this happens to be 2 and you put 2 here, 2 cubed was what? 8. 8 plus 1 is 9. You know that the more the denominator becomes large, the more you have a small value. But in here, if it is 2, it means you are going to have 2 cubed, and that is 8. And 8 here will make this one become a little bit larger than what? This, right? So that's why we reduce the Yn by 1, so that the Sn will be either less or equal to the Yn. So we know that we already have our Sn from the problem that we were given, but Yn, we have to do that here. So considering summation from n equals 1 to infinity n minus 1 divided by what? N cubed, this is the same as summation n equals 1 to infinity n divided by n cubed minus what? 1 divided by what? N cubed. Right? So this we have right here. We can simply say that, you know, this, we can reduce it to have this right here, 1 over n squared minus what? 1 over what? N cubed. Right, so now we have been able to simplify the series, right? We have been able to simplify the series. So we can split the series. Always, whenever you have a series, 2 series in a bracket, right? Just try to simplify it. Split it so that the work becomes much easier for you. So this is the same as summation from n equals 1 to infinity 1 over n squared minus summation from n equals 1 to infinity 1 over what? N cube. So this we have right here, we have been able to split this into this, right? So the next step we are going to do is to consider them one after the other. One after the other. Then we handle it and then we know what we are going to have. So, okay, so considering this summation from n equals 1 to infinity 1 over n squared, this implies that p is equal to what? 2, which is greater than what? 1, right? So we can boldly say that by the p series test, summation from, so by das, so let me write the, so das by the p series test, by the p series test, we say that summation from n equals 1 to infinity of n 1 over n squared converges. So similarly, we can say that summation from n equals 1 to infinity of 1 over n cubed, this implies that p is equal to 3, which is greater than 1. So the same idea, we say that that's by the p series test. So that's by the p series test, we say that summation from n equals 1 to infinity of 1 over n cubed converges. So we say that since the difference, right? Since the difference between the two series, right? They are all convergent, right? So we say that since the difference between the two convergent series is convergent, then we can say that thus the series summation from n equals 1 to infinity of n minus 1 divided by n cubed plus 1 converges. All right, so we have been able to use the comparison test to check if the series will converge or not. And indeed, using the comparison test, it has really improved that, or proven that the series converges. Since the difference between the two series, this and this, converges, then it means that it converged. It has converged, or it is convergent, right? So you can see that 2 minus 3 is what? -1. And -1 is what? Less than 1. So it means that the series converges. So that is the end of the episode 2. I really appreciate your time here, and I would say that we have covered a lot in this episode 2. All right, so rewatch to understand it very well. All right, let me leave this conclusion for this. So therefore by the comparison test, the series the series converges. The series converges, and that is so true. That is so true. So let me encourage you to rewatch, share, subscribe, and please do comment. I really appreciate that part. Do comment. It really helps us to improve on our teaching skills. Thank you very much for watching. I really appreciate your time. Have a good